So if you're traveling into a black hole, okay, two things start to happen. Okay, one, you come to a point of infinite density, and let's just call this let's call that the event horizon, right? As you start moving toward the black hole, you won't notice anything at the event horizon, but it's the point of no return, where it would take all the energy of the universe to pull you back out. Okay? Now, here's the actual event horizon. There's every different type of object has its own event horizon relationship with that black hole, because what we're calling the event horizon is the light event horizon, right? Because it's easier for light to get out because it's already traveling at the speed of light. For us to travel at the speed of light would require tons and tons of energy, and that's being very, very mild. Tons and tons, infinite energy. Right? So as you're like, your event horizon is related to how much energy you can create. Right? If you can create vast quantities of energy, and travel near the speed of light, then your event horizon might be right out here. But mostly we're way outside of that. All right? So two things happen. One, as objects begin to travel at the speed of light, they experience time differently, right? It speeds up time for you, but slows down your biological clock, if that makes sense. Okay, so if you were to go close to the black hole, okay? If you were to go close to the black hole and you're near an area of high gravity, okay, it slows down the clock so that you would experience time. It would seem normal to you, but if you got back outside to me and I've been watching you go the whole time, I may have been waiting for years, right? This is Interstellar did this, where he got back and the guy had been waiting 20 years and they'd only spent a couple of hours on the planet, right? That was close to the black hole. So what's happening is you're time traveling, right? We're always time traveling, and we space travel, and there's a relationship between time and space. Now, when you get to a black hole and you're going in, time and space change positions with each other. They switch, right? So you've got this short distance from your event horizon to your singularity as far as a location in space, right? But it takes you infinite amounts of time to reach it, right? Because at first you're traveling through space and you start traveling through it really, really fast. But then all of a sudden you're not traveling through space really fast anymore. You're traveling through time really fast, and you're covering a small amount of distance in space. And you're going into this black hole. They say that it crunches you, but does it? Does it really? Because the interesting thing is that this gravity well, right, has created a hole, a tunnel into the future, right? So if you were to fall in, it seems like the universe outside is speeding up. Remember how going close by for a few hours and you come back to witness that I've aged 20 years? Remember that? Well, if you were to actually fall in and you were to turn around and look out at the universe as you're falling in, you'd see things get really, really fast out there. But for you, time would be moving very, very slowly, right? You'd be watching thousands of years, millions of years go by, and as you were getting closer and closer to the black hole, it would be like this, and you'd see all the way to the end of time. Because that's how much time it actually takes you to get there. It takes you till the end of time because you're moving fast, right? This is how it's all relative. It's just how you describe it. Are you moving fast or are you moving slow? Well, you're moving fast. You're just time traveling forward at an incredible rate. But we can also describe the same event by saying time has slowed down for you, and you appear to freeze at the event horizon and redshift into non-existence in our universe. So as you're falling in, you're actually moving through time forward. Where does it go? Well, it goes to the end of the universe. That's where it goes. Okay, so now I want to talk about Hawking radiation. And I want to put this out there because I don't understand the logic of Hawking radiation. They've got to be able to describe where it's coming from, where the quantum foam is coming from. Now if you look anywhere in the universe, there are particles. They call them virtual particles, but virtual particles just pop in and out of existence, and they're opposite charge to each other, so they annihilate each other on impact. And everywhere they call it just quantum foam, that there's these particle pairs that are positive and negative that jump into the universe and are annihilated like that. But where are they coming from? I should probably ask Wikipedia before I go any farther. But the thing is that, they say matter can neither be created nor destroyed, but what is this quantum foam doing? Well, we have evidence, bottom line, we have evidence of matter being both created and destroyed in quantum foam. Now we can hypothesize that it's not being created, that it's coming from another dimension, and that they just change, and when they annihilate, they return to that dimension. But that's a theory, right? And it's more complex than the idea that they're just being created. So we don't have a theory as to why they're created, right? And that's where it gets complicated, because we need an explanation, and we haven't observed one. But here's the thing. In a black hole, at the event horizon, same thing's happening, right? I don't know why they talk about the event horizon, because the event horizon of a black hole's got quite a bit of area. Now, this is a fine line where the two particles pop in and out of existence, right? And one of them goes into the black hole, and the other one escapes because they're right on the line. Now, right off the bat, I'm thinking, well, obviously, if there's particle pairs on the line, they're less interesting to me already than the ones that are throughout the center of this diagram, right? Inside the black hole already, inside, there's particle pairs. And not just on that line, right? So that one can escape. Well, what happens when two particles pop into existence right here inside? Well, they both get drawn separately into the black hole, right? Now, Hawking is focusing on the Hawking radiation, which is this one guy that escapes. And he's saying, well, if he's escaping, he's pulling mass from the singularity. But that makes no sense to me at all, how they figure that it's pulling mass from the singularity. It's giving mass to the singularity, right? Because what happens is this particle escapes, right? This particle is added to the black hole. So for every particle that escapes a black hole, one is added to it. And while the one that escapes takes nothing from the black hole, the one that adds to it adds to its mass, thereby making the hole larger and making its gravity more intense. So rather than ending up dead one day, that the black hole will evaporate, according to this theory, it will keep going forever and keep getting larger and will never evaporate. Now these particles here are even more intense, because these particles, because of spaghettification, as you're coming in there, the strong and weak nuclear forces that hold your own particles together, right, get stretched out and eventually broken, and everything is stretched out, right? So you don't go in as according to that theory anyway, you don't go in as an element of any kind, right? Because the elements themselves get broken down into particles, right? And the particles will just become energy, right? So when you've got your two particles that appear inside the black hole's event horizon, they're not able, because of the high gravitational field, to come in contact together. They are spaghettified, which means they're instantly pulled apart, such that they both enter the black hole separately, which means that each component adds to the mass of the black hole because they're not able to annihilate. Well, you might say, well, once they reach the singularity, everything falls together, and so they will be in contact there and annihilate, right? Maybe. But the thing is, when does that occur? That occurs, again, at the end of time. Okay? It's not going to be occurring until Judgment Day, the very last moment of the universe, trillions of years from now. So yes, anything that ever falls in during the history of the universe, from beginning to end, anything that falls into the black hole is technically still in this area here, right? Which is caught up in this arrow of time moving to finality of that black hole, right? Till time stops. And okay, so that brings me right into my little bit of science fiction, which says that our little man, you know, like, he's in a spacesuit or whatever, and he falls into the black hole. Let's say our guy from Interstellar, right? And he's caught up in the thing, and he starts this transit, like, he starts going toward the singularity, right? But we know that time for him has slowed down, And as he sees it, time for us has sped up so that he could actually watch the universe, the history of the universe play out till the end. And you can't actually watch it, right? You can't actually see it because you can't see the light from the universe. It's all dark in there, right? If you were to look out and if you could see, right, then you could see everything play out. But the fact of the matter is the light from that universe can't reach you. So it's dark. Sad day, because you really want that view when it's the last thing you're going to see. Anyway, it would happen so fast you wouldn't even know what happened anyway. So, our guy falls into the black hole. His family cries, right? His friends, aboard the Enterprise, they're all, in disbelief. Oh my gosh, Captain Kirk has fallen into the black hole. We lack the technology to do anything about it. But 1,000,000 years from now, and that's the beauty of it, is because 1,000,000 years from now, he's still in the process of getting to the black hole, the singularity, right? He's going to be there for billions of years, trillions of years. We've got all the time in the world to save this man. Do you understand? He's still stuck. And how do we save him? Well, if we could ever develop wormhole technology so that we open up a wormhole inside the exact trajectory, inside the black hole, on the exact trajectory line, we open up a wormhole to the outside. And then our captain falls into the wormhole before he can reach the singularity, and boom, he pops out right here. And he's like, what took you guys so long? So that's just my little bit of my theory. Now, back to, the Hawking radiation thing. It just wasn't explained to me. Right? It was a question. I've asked a few people. I asked Isaac Arthur, and he gave me an explanation he was confident in. I'm like, am I just not getting it? Where does this quantum foam come from? You've got to be able to show that it and there was some explanation that for a region of space, a cubic region, it contains a certain amount of volume, and that all the quantum foam for that region is somehow related to or drawn from that quantity of space, that cubic volume of space. It just didn't explain it to me. Like, how do you know that? And why? Why are you just assuming that something is able to pull matter from a black hole? Wouldn't it have to come from somewhere else in that region of space? So, whatever back door you're pulling this from the black hole from, if its gravitational attraction is less than the pull to pull it in, then wouldn't it just rip a hole anyway and just, become a white hole on the other side? Everything comes in and goes straight out, but it wouldn't work. So anyhow, that brings me up to the other theory, which is that the white hole is the opposite of the black hole. That's pretty obvious, that it's just whether something is a white hole or a black hole is completely relative to which way in time you're looking. Because the black hole is just an arrow of time, right? It's just moving forward, right? And everything inside it going this way describes the white hole. So it's black from this side, white from that side. Because all the light is going one way. So anyway, Now, if I totally don't get it on the Hawking thing, don't crucify me in the comments, just enlighten me, right? I don't, how am I to know? Nobody's answering the questions that I know. And I'm like, you can't just read articles because they all say the same things. But who's asking this question? I don't know. So if you have an answer to this question, I definitely want to hear that answer. Please explain it to me. How you justify Hawking radiation, that it takes the matter from the singularity or from the black hole itself and then projects it. Yeah, because these this quantum phone, these virtual particles have to originate somewhere, and if we don't have an answer for that, then the question about Hawking radiation just isn't, it just doesn't make sense to me. So anyway, yeah, let me know about that. Tell me that's a cool idea for a movie. You can actually save somebody from a black hole. It would have, but hey, maybe we'll know how to make wormholes. Maybe we'll be really good at it and pinpoint it to the exact point in space and time that it would need to. I mean, think about the calculations. Data would have to calculate where to open that wormhole, right? Everything falling inside. So, yeah, but he could technically do that. He could technically, if they could calculate every single piece of information about the trajectory and the speed and the time and everything that an object fell into the black hole, and then theoretically even millions of years later chart where on that path to the singularity that object will be, and open up a wormhole and rescue him out of there. Anyway, all right. Tell me all the ways I'm wrong. I'll see you in the comments.